Hello and welcome back to my channel. So we're going to try this video again since the last time it didn't have any sound. So we're going to be talking about implicit differentiation. And implicit differentiation is a technique we can use when x's and y's or other variables are together and we don't have just one singular variable to deal with. So we've been dealing with explicit form. And explicit form is just having are two variables, one on one side that is by itself, one of them to the first power, and we have another variable on the other side. Generally, it's x. So we could take the derivative of this function using the rules as we know them normally. Implicit forms is when we have two variables kind of intermingling with each other, or it's when we have something like if y over here was raised to the second power or square rooted or anything else is happening to it besides it being 1y to the first power. So we're going to be finding derivatives. And our derivatives for what we've been doing is slope. So derivatives are slope, and we kind of need to be able to find the slope of more complicated functions to deal with other real-world situations, since we have a lot of times where our different variables kind of play off of each other. So when we talk about implicit differentiation or even explicit differentiation, which we don't normally say, we've been kind of doing this without realizing it. We can write derivatives as y prime, but we can also write them as dy over dx. When I take the derivative of 1x, to the first power, it's always going to be 1. Well, the derivative of y when we have it with respect to x, we're still going to use that same thing. It's 1y to the first power, so we have 1, but y and x don't match up variable-wise, so we need to kind of keep in mind that y could equal another equation. This brings in chain rule. If we have an equation inside of y, I still need the derivative of that inside function being multiplied by everything else. This is where dy over dx comes in. Okay, disclaimer. We could absolutely use y prime, so I could have written this as 1y prime, but if we look at that, y prime and y to the first sometimes can get confused if we write it. So because we have y raised to different powers and different things, we will generally see, and I will exclusively use dy over dx. So the big key here is that we're going to use chain rule without really seeing it a lot of the time, and that's because y could be a function that has an inside. So if I took the derivative of x cubed, our power rule says that we would get 3x squared. If I took the derivative of y cubed, we still get 3y squared, but because we don't know what's inside of y, we still have dy over dx. The derivative of x is 1. The derivative of 3y would be 3. And we're going to multiply that by the derivative of whatever y is, dy over dx. This last one, we have x times y squared. So this is going to be product rule. So the derivative of x is 1. 1 times y squared, so y squared, plus x times the derivative of y squared, so 2y dy over dx. So anytime we take the derivative of something that is not x, we're going to add this d whatever it is over dx, that respect to x. So implicit differentiation, what we're going to be doing is we are going to differentiate both sides of our equation with respect to x. We're going to collect all the terms with dy over dx to one side. It doesn't have to be the left. Factor out dy over dx from our equation, and then we're going to divide everything that's in that parentheses that's being multiplied by. So if we look at what we have here, find dy over dx given x squared minus y cubed equals 0. So the derivative of x, we have 2x minus the derivative of y cubed, 3y squared. We had a derivative of y with respect to x, so we're going to do times dy over dx. Derivative of 0 is still 0. So what we're going to do is we're going to move over are things we want to separate, so dy over dx needs to be on one side, everything else needs to be on the other. This dy over dx is negative, so I'm going to move it over to the other side so it becomes positive. So we have 2x equals 3y squared dy over dx, and we're going to divide both sides by 3y squared. So 2x divided by 3y squared equals dy over dx. So this is kind of like the beginnings of implicit differentiation. They do get more complicated, but everything kind of goes back to those basic derivative rules and algebra.